Swayam Prabha. Digital India. Educated India.
Okay, students. So last class I taught you different enhancement method. Now today again I will teach you the different pretreatment method. This pretreatment means similar kind of. We will use different chemical, different electrochemical method, and let's enhance the catalytic activity. This is also similar kind of thing like tuning the electrocatalytic activity and use them for biosensing applications. So let's continue again like different tuning method, how we can improve, and these improved activities also may not stay for longer time. This is the another phenomenon I will cover today. So what is the main concept for today's lecture? First, let's come to the tuning methods that I taught last time, like sodium borohydride on chemical method for tuning. Today I will teach you some other methods, and one part that I will add, this high activity, if you want to store for longer time, that may not be possible, that can decay, that can change with time. So then what's the reason for this changing, that also I will let you know. So this dependence of catalytic activity of the pretreatment also is depend on the aging behavior, means with time this highly catalytically active phenomena may be changed, right? That phenomena, that's why you have to be careful. So you should have this kind of information. So this is the main key points of this lectures is the pretreatments and the aging of the electrocatalytic activity. So what's the aging? Aging means, so as I told you last class, so if you have some suppose gold nanomaterial, gold nanoparticle modified surface, and you measure here like hydrogen peroxide oxidations after the enhancement, right? So you got the very high catalytic activity, right? This type. At the beginning it was this type. This is cyclic voltammogram. So in the y-axis current, x-axis potential. Now if you keep this on for some time like 1 week, now you have to check this catalytic activity. I mean, by measuring just a cyclic voltammogram you can check their catalytic activity. You have to mention the electrocatalytic. This is not just a catalytic, electrocatalytic activity. Then you say 1 week you can check. You can check after 1 month, then after 3 months, after 6 months. Then you have to check this kind of cyclic voltammogram. You may observe this cyclic voltammogram slowly decrease with time. So you improve first. So it was very beginning, its catalytic is like this. Then you increase the activity from 1 to 2 up to here. This is called the enhancement by sodium borohydride. Now if we keep for longer time in your laboratory environment, in your room temperature, then slowly this can be decreased. So this is called aging. Okay, so let's show you this one schematic for this enhancement and decrease of this electrocatalytic activity and what's the reason. See, you can see that first time I told that gold, you have a electrode surface that modified with gold, but this gold nanoparticle can be synthesized in different way, right? At a very, I think few class before I already taught you, like we can go for the chemical reduction, chemical reduction method. So we can use a gold salt like chloroauric acid, HAuCl4. Here gold oxidation state is 3, that's why I put the Au3 here. So, chloroauric acid, and we can reduce this one by using chemical. So, what kind of chemical? Some reducing agent. So you need some reducing agent. See, so some reducing agent we can use, like for example here I put citric acid, sodium citrate, ascorbic acid or some ascorbate salt, sodium borohydride. So these all three, they are the reducing agent. This all three the chemical process. Chemical process. What chemical process? Is chemical reduction process, and we can deposit, we can this chemical process mean in a beaker. Maybe if you use your chloroauric acid HAUCl4, and then if you add this reducing agent, so you get a reddish or pink solutions of the gold nanoparticle. Now what you have to do on a electrode surface, maybe you have the dendrimer, or maybe you have some other linker, maybe mainly if you have the amine modified surface, if you have amine modified surface, and if you drop this gold nanoparticle in this surface, then amine and gold, they have some interaction, and easily gold nanoparticle can be attached on your electrode surface. So you will get a gold nanoparticle modified electrode surface that you can use for biosensing applications. Clear? So this is the chemical method. Now let us come the electrodeposition, that also I taught you, right? Let us show you one more time. Electrodepositions means, so you have a electrode surface on this bare surface, and this bare surface you should have a solution of chloroauric acid, HAUCl4. Then you have to apply here a negative potential, suppose -0.3 volt. If you apply, then this gold -3 to it will come to AU0, means gold 0 stage. Then nanomaterial will be, means this is in situ. So this is the ex situ, this is in situ, means on inside solution when you apply some potential, then this nanomaterial will be deposited. What is the here driving force? Is the negative potentials. This is called electrodepositions method. Using this method you can deposit this nanoparticle. So here just I give the example of gold. You can try some other salt, means metal salt, and those metal you will get as the form of nanomaterial or nanoparticle form. Now we will try the oxidations of the like hydrogen peroxide or formic acid. Some oxidation we will try on this sensor surface. So if we see, this is very common method. You can if you have the lab facility, you can check also. Just after synthesis, citrate, ascorbate, sodium electrodeposition, just after synthesis, if you check their electrocatalytic activity, you may get very high catalytic activity, because you will get this kind of very high signal like hydrogen peroxide or formic acid. If you measure electrochemical signal, you will get very high current, and the potential, oxidation potential will be very low. This is, I am saying that just after synthesis, after synthesis. Now just after synthesis, you modified your electrode on the gold nanoparticle like this, and keep it in the room temperature in the laboratory environment for longer time. This is called the aging. You may see the activity somehow it will decrease, that we observe, that we may observe. Also it depends on which environment you are storing. So there may be one problem, you may think that this activity decrease may happen due to the contaminations, right? In the open air, if you keep, there is some other carbon contaminant, right? They may come on the sensor surface, on the, so there is so many active site of the nanomaterial, right? These active sites of the nanoparticle, they can be blocked by carbon material or some other contaminant from the open air. So you can try to store, that's why this kind of sensor surface inside a solution. If you store it, means if it is just a bare gold nanoparticle coated sensor surface, or just a gold coated surface, then just try to keep it inside the solution you can store. You can store it. Then if you check after long time their electrocatalytic activity, like after 1 week or after a month or after 6 months, you may see this decrease of the catalytic activity slower than the open air. This is one of the causes, the contaminations. And another reason, as I told, when you go, if you have a like nanomaterial coated electrode surface and you are getting very slow electron transfer rate, means your electrocatalytic activity of your sensor surface is very low. So you want to tune its activity, you want to go to the high electrocatalytic activity, then you can add just sodium borohydride. So then you can get again fast catalytic activity. So why this happened? Because hydrogen can be adsorbed on this surface also during the sodium borohydride treatment. So in this case also, because of surface reconstruction, surface strain, you may get higher activity. And when you keep for longer time, but during the aging, this surface reconstruction again slowly it may come to the ground stage. So there may be some strain on the surface that called surface reconstruction, then again it may come to the slowly ground stage, and because of this also electrocatalytic activity will decrease slowly. So two reasons possible, one is surface reconstruction and another is the contamination. So how you are storing the electrode, that is also very, very important. So if you keep just open air in dirty environment, that is not ideal case to keep the high catalytic activity for the electrode surface. It can be decreased. I will show you the example now. See, this is the surface just after modifications. This is the ACM image, scanning electrode microscope, that image. See, you can see the small nanoparticle, it is size around 10 nanometer, all the gold nanoparticle coated. Now, it can be just after synthesis or just after sodium borohydride treatment. You can see this is the high activity, this is this one, you can see the oxidation peak potential also very low, current also very high. Now, when you keep for longer time like 1 week, 1 month, 6 months, see the activity, this peak potential is shifting towards right, and current also, see in this potential, see current decrease, this much current, and again if you see, say here, so peak shifting and current also decrease, this shifting, current also decrease. So it means this is because of aging, and it means your catalytic activity decreases. So there is so many, you can see that this kind of diagram, this curve. So this all the things actually tried just after citrate method, ascorbate method, sodium borohydride method and electrode depositions method. So here you can see just 1, 2, 3, 4. So these all the methods just we tried just after different procedures, means you can try all the synthesis procedures like chemical procedures, electrode deposition procedures, you may see similar behavior. At the beginning you may get high activity, then slowly it may decrease. Now let us come some other factor, means if catalytic activity decrease with time, then one method is the chemical method, that is sodium borohydride can be used. Let us use some other procedures also. Second method I will teach you now, that is electrochemical method. What is this electrochemical? This is electrochemical method or electrochemical cycling. Electrochemical cycling you can try. This electrochemical cycling, there is different kind of electrochemical cycling. So one very important method is the anodic treatment. I will come this treatment. You may tell this is the a kind of pre-treatment. There is, you don't need any kind of reducing agent, but this is just a potential cycling method we will try, and it can improve the activity. Let's show you. So suppose you have this kind of electrode surface. Okay, so your electrode surface is coated with gold nanoparticle, and so what electrode surface we are using here? Indium tin oxide coated electrode surface. So this is a linker, and we tried the gold nanoparticle, and you can see that gold nanoparticle can oxidize hydrogen peroxide forming acid, but at the beginning we are getting slow. Now when we try the anodic treatment, what is this anodic treatment? Anodic treatment means plus minus. So suppose you have to use a 0.5 molar sulfuric acid solution. Means anodic means oxidations, means on your gold nanoparticle coated surface you can try a higher potential window. This cycling you can try. Suppose you can try like 0.22 around 1.5 volt, this volt to this volt. Then if you cycle in the 0.5 molar sulfuric acid medium, you may get something like this. Something like this means your gold can be oxidized at the higher potential. Your gold surface, your potential cycling in a sulfuric acid medium, then it will form gold oxide. Then gold oxide again reduce. Then this you can go like 20 times, 50 times you can try. So first during the anodic scan, you know, right, when we go from left to right, this is called anodic scan, right? Anodic scan. So this is called, that's why anodic treatment. So in the higher potential we are scanning, and gold oxide AuOx we are forming. So if that's why you see in the schematic. So here a gold nanoparticle, one gold oxide layer will form during this treatment. And when this gold oxide, when you reduce, then this gold oxide again, this gold oxide reduce back here, and during this potential cycling, this gold surface will show high catalytic activity. This is again because of kind of surface reconstruction, because this potential scan, again the surface energy can change. This is the assumption, just surface reconstructions, but you may see the gold oxide oxidation reductions also on the surface. This may further improve your gold coated surface electrocatalytic activity, you can improve. So this is called anodic treatment or electrochemical cycling. This is another pre-treatment. Another pre-treatment. Now this highly catalytically active sensor surface, now let's store again in the room temperature for some time, for a long time. There is a possibility of decrease of the electrocatalytic activity again. Let's show you something. So here is the data. So you can see when gold nanoparticle at the very beginning, so you may get very low catalytic activity, and then you can go for the first scan, second scan, see first here gold oxide forming, and then gold is actually reducing. It is actual data. Now see here the formic acid oxidation. So formic acid oxidation we tried when before anodic treatment and after the anodic treatment. You can see this one is the before anodic treatment. See, formic acid oxidation is very low, but if you go for the anodic treatment, you can get the highly catalytic activity. Now if you keep it for the longer time, like 1 week or more than 1 week, 1 month, 6 months, you can see the activity actually decreasing. Okay, so this phenomena you observe. Now let's show you some other pre-treatment method so that we can improve the catalytic activity. So this is all the pre-treatment method. Sometime you may see, maybe after some class I will show you some scanning image or some AFM, atomic force microgram image, means you can see the actual sensing surface. If there is some contamination, is after this pre-treatment is actually contamination is removing, or not, if surface roughness changing or not. These all the characteristics also I will show you next class. So today again I will going to show you some other treatment. Let's cover all the treatment name, then how we are improving. Then I will come step by step. We will focus the surface images, the kind of change you can see after the treatment. So there is some possibility. So one big possibility after the treatment or pre-treatment or after this anodic scan, anodic treatment, the why we are getting improved activity, there may be a contamination removal. Another thing that we are saying surface reconstruction, but that is just the assumption. But surface, if it has the contaminations, and after the treatment if you can remove and if you get the higher activity, that image if we analyze the surface by AFM or SEM, then definitely you can see by AFM you can see the roughness change, but SEM also you can see the clear image of the surface that if there is a contamination present or not. That I will show you next class. So today let's cover some other treatment. This is treatment and I will show you some actual data and I will compare all the treatment. Let's compare. Today I am going to show you, here you can see like total 6 pre-treatment of ITO electrode. ITO means you have a glass, ITO means glass surface with indium tin oxide coated nanoparticles, right? As I told you, when you receive this kind of electrode from any company and any industry, they have lots of contaminations and they cover the active site of the sensor surface, so we have to remove them. So how we can remove? So we tried different process, 1, 2, 3, 4, 5, 6 different process I will show you. So definitely you should have a control experiment that is called no treatment. So one electrode we will check just after when you get the electrode from company, from any industry or from any vendor, any source. Let's check the cyclic voltammogram by using a formic acid oxidation, any hydrogen peroxide oxidation, glucose oxidation, and let's get the cyclic voltammetry. That will be your control experiment, control data, and then compared with other treatment. So we compare here. One method is the 1 molar hydrochloric acid. So you can take in a beaker 1 molar hydrochloric acid. Then you can dip your small ITO chips. You can dip for 10 minutes. Then throw all the HCl and then wash it with the DI water. DI is water, very clean water. Then clean the ITO surface, all the indium tin oxide coated glass surface you can clean. Then measure again cyclic voltammogram. Then you can see the change and then compare with the control data. Third method is the dipping is 1:1:5 hydrogen peroxide, ammonium hydroxide and water mixture, and we can heat this solution for 70 degrees Celsius. This cleaning method I already taught you at the very first class. So if we clean this surface by using this chemical, this is very I mean you can say very important treatment method. They can remove many contaminations like organic contaminations. So like you can take a beaker and you have to take hydrogen peroxide, ammonium hydroxide and water mixture. So this mixture 1:1:5 ratio, and then heat this solution at the 70 degrees Celsius for 1 hour with your ITO chips. You can put all the ITO electrodes here and heat it. Now after that bring the room temperature, clean it, and after the cleaning let's check again cyclic voltammogram of formic acid or hydrogen peroxide. Then compare with your control data. Okay. So this is another method. Fourth treatment you can try this hydrochloric acid treatment, and after that you can try this treatment. So after hydrochloric acid treatment, maybe we may think that this is may not good enough for removing all the contamination. Then 1 plus means 2 and 3 both you can try. Then let's try to see if both they can make further improvement of the electrocatalytic activity or not. So, treatment 2 followed by the treatment 3. Now, we can show another treatment, that is again there are some chemical treatment. We can take your ITO chips in a ultrasonic bath in a methanolic solution that contain potassium carbonate. So, in a beaker also you can take in a methanolic solution that contain K2CO3, and you can bath sonicate this one for 30 minutes. Then clean this one, then again check the cyclic voltammogram of formic acid or glucose or hydrogen peroxide, or whatever you choose the substrate. This is another. Then another treatment, you can dip this 1:1:5, and this method you can try, and water, and you can increase the time at the 70 degree. Means last time we tried for 1 hour, you can increase 1.5 hour. After sequential ultrasonications of the trichloroethane, ethanol, water, means that's also another cleaning. Means what you can do, your all the ITO chips, first you can clean this one with some acetone or trichloroethylene, when they are very much non-polar solvent. That also I taught you at the beginning, that you can try first. Means in a beaker you can take all the ITO chips, put it acetone or trichloroethylene, sonicate it for 15 minutes, wash it, then take again ethanol, sonicate it for 15 minutes, wash it again, and take the again water, sonicate it 15 minutes, wash it. Then when this is the many steps washing and cleaning. Then after that all the chips, after this cleaning, you can take 1:1:5 ammonium hydroxide, hydrogen peroxide and water mixture 1:1:5 ratio, and then you can heat this solution for 1.5 hour at 70 degrees Celsius. Means we tried very strong cleaning now, and we can compare those all the data, and we can see that further where we may get the further improvement. So, treatment 1, 2, 3, 4, 5. So, we just compare all the things. So, we saw that last treatment actually it is showing, you can see here actually we checked this just a buffer solution, just a buffer, and here we use potassium, we tried the reduction then oxidation. So, this is K3 FeCN6, this is I don't know third stage, right. So, here we first tried reduction, right, this is the reduction, then oxidation. See, in the case of potassium ferricyanide, in this case we tried all the treatment, but we did not see much observable change. But means why in this case? Because your all the electrodes may be not that much contaminant, but some electrodes case if it is contaminant, then electrode means if it is very much contaminant, then treatment 1 may not be effective, but you can see that treatment 5 is very effective. Means I can say from here treatment 5 is very much effective to remove all the contaminant. You can try others, but treatment 5 is the very much effective for here. And you can see here also some data. So, we observed treatment 1, 2, 3, 4, 5, and here also we can see the observable change, but some cases HCl actually show the very high cleaning. But one thing just you have to remember that some cases you may get that HCl can remove the maximum contaminant, but some cases may not. But in the last method, that 1:1:5 mixture, the hydrogen peroxide, ammonium hydroxide and water, just after sequential ultrasonication of trichloroethylene, ethanol and water mixture for 15 minutes sonication and then dipping inside this is a very good cleaning method. And they can remove maximum organic contaminant, and you may get very high catalytic activity after the removal of this contaminant. And if you store again for the room temperature for some time, this activity also can be decrease, activity can be changed. So, this can be happen because of again contaminations, because from the air again some contaminant may come and they can cover the active surface. Okay. So, these things you can we should remember during the biosensor formations. So, what is the conclusions of the today's talk? So, we can use different pretreatment method to improve the electrocatalytic activities, and this kind of improved activities may not stable for longer time. If we store for the longer time in the room temperature, this activity can be decay. This effect is called the aging of the electrocatalytic activities, and this is because of another reason also, surface reconstruction or maybe the contaminations. This is the factor. So, thanks. That's all for today. So, next class again I will teach you some other methods of enhancement and use for the biosensor application. That's all. Thank you.